At the end of the second lecture, we planned, which is as you can see in the schedule, half an hour of discussion. So between 12:30 to 1. So if you are interested, you can just stay here and there will be some discussion. And then the second announcement is that there is, in connection to the Dirac Medal ceremony, there is a huddle which is organized by Valentin, Ellie, Atish, and Neil, where Atish is the director and 3 postdocs, about entanglement entropy. And today in the afternoon, starting at 2, there are a few talks. So if you are interested, you are welcome to join this activity, which is not happening here. It's happening in Euler lecture room, which is on the same floor as the cafeteria. So on the other side of the cafeteria, if you exit from the terrace, you go to the right, and there is this new room. So in case, if you don't find the way, either come to Valentin, which sits here, or to me, and we will direct you there. Okay, so today we have as a first lecture the another Dirac medalist, who is Horacio Casini from Istituto Balseiro, who is going to talk about modular invariance as completeness. Please.
Okay, thank you. Is it working? Is it working? Okay. Well, I will talk about this modular invariance and completeness, this connection of 2 ideas. One is modular invariance, and I thought, as this is a school on strings theory and modular invariance is very important, this would be a good topic for this school, even if my modular invariance is all about conformal field theories in 2 dimensions. What? Maybe my thing? Okay.
Maybe it's
right there? Okay. I mean theories without gravity in 2 dimensions, so not strings. And connecting this idea with completeness. Completeness is kind of an idea that is valid for quantum field theories in more dimensions, and people think this idea of completeness, for example, Maxwell field, pure Maxwell field is not complete. It will be complete if you add charges, electric charges and magnetic charges that obey the Dirac quantization condition. Is somehow an idea of how much you can increase your theory. But here I will define this in an algebraic way, try to understand how to define it precisely in any dimensions, and then connect these 2 ideas in 2 dimensions on conformal field theory in 2 dimensions. So this is a paper of last year with Valentin Benedetti, that was a PhD student at Bariloche and now is here. I'm grateful that he's here to answer the questions. And then Javier Magan, that is a researcher in Bariloche, and Kawashigashi and Longo, that are 2 mathematicians working in Japan and in Rome. So this is a plan of the talk. I will start giving a definition of what I think is a precise definition of completeness in quantum field theory as something called Haack duality. And this is an algebraic notion. And then I move to modular invariance. I restrict attention to this S transformation on the modular invariance. Modular invariance, perhaps you have already heard about this in this school in the Berlin talk. Is, for example, if you have a torus, it's just saying that the partition function of your torus is equal if you change the sizes. Say you put this in the other position. These 2 partition functions are equal, and this looks like very much natural and completely trivial from this picture, right? Because you are doing partition function of something that is the same. But we will see that it's not always holding, even for completely sound conformal field theories. And then we want to understand what does it mean in terms of the quantum field theory itself. And I will show how this is related to completeness through some properties of these range entropies. Then I will go through measuring the amount of incompleteness in theories that are incomplete, and this will give us a global index, some numbers, some specific numbers that measure this amount of incompleteness. And I will apply briefly this to some ideas on minimal models. Minimal models are conformal field theories with central charge less than 1, and to see how these ideas can be used to make selection rules for the renormalization group flow that flow from one minimum model to the other. I will briefly discuss then some infinite index cases, and then some results that can be generalized to higher dimensions. So let me start by defining the things that I'm interested in here. One is this idea of completeness. So for this, I will start by defining what is a non-local operator. Non-local operator, suppose you have a region like in higher dimension, say some tube, some ring-like region like this R here, and then you draw, for example, a Wilson loop inside. So this operator can be said to be localized inside the region R because it commutes with every field operator, every local operator outside, right? So it's localized inside, and this, we will say that it's inside this region. But there is another notion of locality. There is another notion of saying that this operator is inside the region that is different from the previous one. That is the fact that this operator could be or could not be produced by local field operators inside the region itself. Typically, a Wilson loop, for example, in Maxwell field, is not local in this sense because it cannot be produced locally by electric and magnetic fields, gauge invariant fields, but in order to write it, you need to exponentiate the integral of the A mu field, and the A mu field is not a local field. It's not a well-defined gauge invariant field in the theory. But still is local, the Wilson loop is local in the previous sense because it commutes with electric and magnetic fields outside. So there is two notions of locality that are different. And when an operator is local in the first sense, but not local in the second sense, so it's not produced additively by local fields inside, I will say that I will call this a non-local operator. So to give more formality to this idea, we can produce an algebra inside this ring that is called the additive algebra. That is the one generated by all balls inside, so all field operators inside, let's say. And this is kind of a minimal algebra that you can have there. But you can also produce another algebra that is the algebra of operators that commute with local operators outside. Here outside, I call it R prime, the outside part. So you take all operators that commute with the fields operator outside. This includes, for example, the Wilson loop. And this algebra, in that case, it will be bigger than this other one. So, and this we call the maximal algebra. It's the maximal algebra that respects locality in the theory. And then you can have the situation that you can have two different macroscopic, physically different algebras attached to the same region, to this region R. And when that happens, you can see mathematically that something interesting happens, that when that happens, the same happens for the complementary region. The complementary region R prime here, in 4 dimensions, this complementary region is the complement of a ring. It's topologically also a ring. And then in this case, you have also non-local operators. If you have non-local operators for some region R, you have non-local operators for the complement. These, in general, are different sets of operators. Here, for the Maxwell field, this will be, for example, a Wilson loop that is a magnetic flux, and this other one is called a Toff loop, for example, that is a flux of electric field. And you have the two complementary algebras, dual algebras, and it always happens in this case that these A's and these B's that are non-local operators for complementary regions do not commute to each other, cannot commute to each other. So this idea here, algebraically expressed, is the same idea of generalized symmetries. So it's an algebraic description of generalized symmetries described in this way. So then the idea of completeness is very natural in this perspective. What is completeness is the fact that the algebra generated by field operators in some region is the maximal one compatible with causality. So completeness is the identity between these two algebras I was talking about. One is the additive algebra, and the other one is the maximal, that is just the commutant, the thing that commutes with everything outside. So when these two things are equal, we will say that there is Haack duality. Haack duality for this particular region, right? For the additive algebra. When there is Haack duality, we say that there is completeness on the theory. So the idea is that the local operators is an algebra large enough, have enough operators such that the commutant of the outside is exactly the same thing. You know, otherwise you could think you could still add something more to the algebra and still respect locality. And this idea is the same that people have been studying in the past or thinking in the past about the idea of completeness. For example, if you have a Wilson loop, you can try to complete this theory by adding charges. If you add a charge, you can produce Wilson lines that you have the line connecting these 2 points, and then you have charges in the extremes. This is called a Wilson line. And this operator can be used to break the Wilson loop into pieces. So the Wilson loop that was a non-local operator, in this way, is transformed into a local one. So you destroy the non-locality of operator. Yes?
So in a quantum field theory, we have two kinds of non-local operators. The topological non-local operators, which are associated with the generator of the generalized symmetries, and the generic non-local operators, which are not topological. So I guess here, when you say absence of non-local operators, we are imagining the topological one.
Yeah, I think...
how do you see the distinction from this algebraic point of view?
Sorry?
How do I see the distinction? I didn't see where the topological nature of the non-local operator enters into these considerations. I didn't get it.
No, well, behind all these things, there is the idea that, for example, if you have the Wilson loop, this Wilson loop can be deformed by local operators. You can deform the ring by local operators, additive operators, and you can produce non-local operators in other regions, bigger, for example. So in that sense, it's topological. It's the same idea, right? It's the same idea. The local algebras can be used to deform the non-local operators to other non-local operators for different regions. But the second class of operators that you mentioned, what was that?
No, I mean a generic Wilson loop, if you change its sides, you get another correlator. It's not topological. While the absence of uniqueness, absence of generalized symmetries means absence of topological operators. So I mean, that's what I mean. So
if you change the size, it's a different operator, but it's still a non-local operator for the new region. That's what I'm saying. In that sense, maybe people think in this term, in these things, in the Euclidean formulation, and then they think operators that if they are alone have, let's say, unit expectation value. They are nothing. So maybe this is what you. I think what you have in mind is Wilson loop and Wilson loop dagger. Both of them give you the identity, and this in Euclidean can be thought as two things that go together or something like that. So here I'm thinking always in the real-time formulation, right, for the operator. Somehow
we can discuss later.
Okay. Then this is an example where you can complete a theory just adding charges, let's say. So and this the same idea of people have of completeness of gauge theories, that you have enough monopoles and electric charges, the maximal set of electric charges and monopoles that obey Dirac quantization conditions. Well, exactly the same idea is the idea that kills the Haack duality violations, that makes all the algebras Haack dual, let's say. So in that sense, this idea of completeness is the same idea that people have been thinking about in gauge theories. And here I have another example that is more similar to the one that I will be using in this lecture, is the case of you have a theory with some gauge, with some global symmetry group, and then you produce another theory that is just taking all the neutral operators of the original theory. So you make the quotient of the original theory by the group, and this contains only the neutral operators. For example, in that case, you would have a region of 2 balls, and a non-local operator for these 2 balls will be a charge operator here and anti-charge operator there. Charge and anti-charge is neutral operator, but it cannot be produced locally in the 2 balls. You need a charge here and anti-charge there, and this cannot be produced locally here. It's not additive here with here, right? And in the complementary region, automatically there is another non-local operator that is the twist. The twist is an operator that implements the symmetry group, but only in a region. In this case, in this ball here, right? So, and this twist will not commute with this charge-anti-charge operator because it will transform the charge here. So these are the 2 complementary or dual non-local operators, the twist outside and the charge-anti-charge in the 2 balls. It's interesting that in dimension higher than 2, this type of non-local operators that are attached to regions with disconnected regions is completely classified, and it's always coming in this way from a group just taking the quotient of a theory times the symmetry group. In 2 dimensions, the possibilities of, in 2 dimensions, it would be 2 intervals, and then the possibility is greater, and there is not necessarily a group behind these failures of Haack duality. You can have non-invertible symmetries. So some remarks. First, the idea that is very important for this talk is that a non-local operator is a relative notion. For example, a non-local operator, a Wilson loop, for this ring-like region here in 4 dimensions, is a non-local operator, can be a non-local operator if there are no charges associated to this Wilson loop. But it still is a local operator considered inside the ball. Because, for example, you have the magnetic flux is the Wilson loop in this ring, but the magnetic flux is just produced by the magnetic field inside the ball. So typically, all non-local operators of any theory are local operators in topological balls. So this idea of non-local operator is always associated to some region with some special topological properties that is non-trivial. So the ball usually has has known non-local operators. And this is called Haack duality for balls, and it has been proved for many, many under very simple assumptions. So, but this same idea tells us that all non-local operators, like Wilson loops, Stokes loops, etc., are ultimately produced by field operators, in the algebra of field operators, of local operators. Then one can think, well, another description of quantum field theories, there is not this algebraic description, there are many descriptions. One description could be this bootstrap description, in which one uses the dimensions, for example, in conformal field theory, uses the dimensions of all primary fields and the OPE coefficients to define somehow the theory, right? So it means that this data, this conformal data that applies only to local operators, field operators, should have all the information. There is no new information coming from this idea of non-local operators or, in algebraic terms, Haack duality violation. So it means that if you have a theory with non-local operators, Haack duality violations, there should be an imprint in the conformal data, in the bootstrap data, that tells you that information, right? Well, one idea would be, natural idea would be how to extract from the bootstrap data this property. When the bootstrap data tells you that you have a non-local operators or not, right? But it's a difficult question because it implies to understand somehow something about non-local operators in terms of local ones. So this is the question we want to address, how to see the imprints of generalized symmetries in the bootstrap data. For example, the simplest question would be if you have a CFT, how you know that this CFT is not the neutral part, is or not the neutral part of a bigger CFT under taking the neutral elements under some global symmetry group, right? And it's not evident at all. The converse question is simple. If you have the bootstrap data of the theory with a global symmetry, you can check that this symmetry is there in the dimensions of the fields, in the OPE coefficients. But it's difficult to understand if this can be extended. The theory can be extended to a bigger theory through that has charges, let's say. So the question then is this one. And what I want to talk about is that this idea for two-dimensional conformal field theory can be answered. And the answer is simply that this completeness is equal to the idea that there is modular invariance, in particular this S modular invariance. There are two modular invariants, the S modular invariance that this connects these two torus, let's say, and the T modular invariance that in the context of what I'm saying, I'm talking about always about quantum field theories, conformal quantum field theories, not a statistical model, let's say. This T modular invariance is always there because it is associated to the locality of the fields. I'm always talking about local quantum field theories. So how to make this connection? Well, these connections have been made some time ago. The first one that proposed it was Rere in 2001. And there are some unpublished proofs by Longon, Kawashibashi, and Muger. And somehow this was how our collaboration started, because we came to this idea, to this connection, using range entropies that connects the partition functions to the replica trick. The partition functions have the idea of modular invariance inside. So you connect the partition functions with, with the range entropies through the replica trick, and the range entropies have some insights on the nature of algebras, on this nature of Hug duality. I will show that. But then we have this idea, but we look at the literature, the algebraic literature, they already have somehow these statements in many papers, but they refer to other papers, and to other papers. At the end of the chain, you find that there is no paper with the proof. So we asked Roberto Longo, where is the proof? And he said, oh, we didn't publish it. And then they associated with us and produced our paper that have two parts, one going through the range entropies with a physical proof, and then there are mathematical proofs using this superselection sector theory. So I will go, of course, by the way of the range entropies. Well, range entropies are information measures. If you take a density matrix, you make powers of the density matrix, take the trace, the logarithm, multiply by this number. That is a conventional thing, and this is the range entropy. When this n goes to 1, it's just the usual von Neumann entropy. The reason why these are interesting, is particularly interesting, is because they are associated to some nice partition functions when the index n is an integer. This is the replica trick. For one interval in conformal field theories, this is known from long ago by the paper of Calabresi and Cardi, and then for two intervals, and it's very universal, it only depends on the central charge. For two intervals, it has a lot of information and are difficult to compute. But for two intervals, it is convenient, instead of using just the entropy of the two intervals, to subtract here the entropy of the single intervals. In such a way, one kills the divergences. This epsilon is a cutoff, so this kills the divergences, and the result is completely finite, and it's finite and depends on only 4 points in the conformal field theory. It depends on only one number. Only one number that is called the cross ratio. That is this number here, this particular combination of the position of the points. So this quantity is called the range in mutual information, and you can write capriciously in this way. This is a function, so it has all the liberty, all the freedom of any function like this one, but plus this that depends on the central charge, and it's useful to write in this way because of the following. Suppose you have the real line in the conformal field theory can be mapped to a circle, so I can have two intervals, I1 and I3, and the complement is I2 and I4. And then if the entropies of complementary regions I1 and I3 are equal to the entropy in the complementary region, I2 and I4, then you can go through a simple calculation and show that this is manifested in the range in mutual information in the quality of this function, this symmetry property of this function unx equal to un 1 minus x. And then you can say, well, this is always the case then, because the entropies for complementary regions are always equal. This is what people have in mind. But this is not true. This is the thing is, this is not true, because in quantum mechanics, the entropies in a global pure state are equal for complementary algebras. So the algebra and the A prime is just a commutant. All operators that commute with the algebra A is another algebra that is called the commutant. And what you can show is that in the case of the global pure state, these two entropies are equal. So whether this property is true or not depends on whether the complementary regions correspond to complementary algebras, to commutant algebras. So in that case, as we have said, what you have is Hug duality. When you have Hug duality, you have this property for two intervals. But as we have said before, for theories that are not complete, you can have situations where these two algebras do not correspond to the algebras of complementary regions. So this property tells you completeness and Hug duality for the case of two intervals in the conformal field theory. So we are interested in the case where there is no this property, when there is no completeness. One example simply, yes.
Can you remind me what is the entropy of an algebra?
The entropy is a mathematically precise way to say when you have typically one says you have a Hilbert space that is a tensor product of two Hilbert spaces, and you make a trace, and you make it the reduced density matrix, and you evaluate the entropy, the von Neumann entropy of this density matrix. Well, there is somehow a generalization to that, saying that that is more appropriate to more general cases like quantum field theory, that you reduce to an algebra. So in that case, what is the density matrix? The density matrix is the only operator of the algebra itself that can be used to evaluate expectation value of operators doing the trace, let's say. This is always thinking with a cutoff. We have a cutoff in mind because otherwise you cannot talk about the entropy because there are deviations. That is why I'm talking about subtraction of entropy. So there is a lot of technical things that are not important, are really not important here. But it's important that you can do it in a lattice. So this is nothing to do with the continuum. In a lattice, there are this model exactly, you can produce it in a lattice, and then you have these Hug duality violations, and then you have an algebra that in the two intervals you have something local there, some, let's say, field operators attached to some points, and then you have something crossing the two. Let me see here. For example, this is a chiral scalar. A chiral scalar is just the derivative in some null direction of a massless scalar in 2 dimensions. And you can think also this as, people call it the current, because it's exactly the same theory as taking the current for a Dirac field in 2 dimensions. And then these are the commutators. So it's a Gaussian theory, quadratic. Everything can be computed. And then in this case, what you have is that given the current in 2 intervals, if you take the commutant of the outside part, you get another operator that is just the integral of the current crossing from one interval to the other, passing through the outside part. And it's immediate that this operator will commute with the outside part because it's just the field, the scalar field in one region minus scalar field in the other. So these are non-local operators of this theory. And you can see that if you take the commutant, for example, of I2, I4, you get the current here, and you get this operator crossing there. So there is no Hug duality. And you can, these are all Gaussian fields. You can put it in a lattice. You can compute entropies in the usual way for Gaussian fields and check that. And you can evaluate, even analytically, this U function. And this is the form of the U function in this case. It goes to 0 for the cross ratio going to 0, because this is a limit where the two intervals are very far apart. So the mutual information goes to 0, everything goes to 0. It always goes to 0, the U function there. But in the other extreme, going to 1, the cross ratio going to 1, this diverges negatively in a certain fashion. So there is no Hug duality, and this is manifested here in this calculation. Yes?
Okay, I guess that one finds out from the J commutations, but naively, specifically because 013 is localized in X1 and X3, and 024 is localized in X2 and X4, which are space-like separated. I'm kind of surprised that they don't commute with each other.
They don't commute with each other because this is a null line. It's a null line. It's not a spatial line. So this is a chiral theory. So X here is a null line.
Okay.
So this field phi is a kind of, yeah.
Okay, so here we are not parameterizing the spatial interval right now with these intervals. We're actually placing this thing at along the geodesic, let's say.
Well, it's the same for spatial intervals because this spatial interval will be mapped to pieces of the null line, right?
Yeah, so this closed interval is parameterizing X plus.
Yes, you can say.
Okay, thank you.
So you see the commutator here. So these fields do not commute, have a delta prime commutator. So the replica trick, the replica trick is just a trick to compute these range entropies. Here is for one interval, you take the density matrix, is represented in the path integral. You have the plane, the Euclidean plane. You have a cut along the region where you want to compute the range entropy, and you have to produce copies of this. In this case, 3 copies because this is the range is 3. And then you have to glue these copies along the cuts. The upper and the lower cut are the places where you put the boundary conditions to evaluate the value of your density matrix. And here you have to glue these things because you are doing powers of the density matrix, and then you glue the final cut with the first cut to do the trace. At the end, you get a partition function in a manifold that is described by these 3 copies glued in some particular way. The thing has some conical singularities in the boundaries of the interval, let's say. So this is the replica trick. For n equal to 2, so 2 intervals now, we'll have to do the same, but for 2 intervals. And in this case, you have the fact that the genus of the manifold is 1. It means that it has the same genus as a torus. So this is why n equal to 2 is important in this particular case. It has the same genus as a torus. And then you can conformally transform this manifold to a square torus like this one. And this has been studied ago by some people. In particular, you can see this paper. And this conformal transformation gives you some universal piece that depends on the central charge for the partition function that give you some number here, some particular logarithmic term, plus the partition function of the final torus, the square torus. The square torus. So you can compute in this way the range G2 of any theory if you know the partition function on the torus of theory. So this is a particular case that has been studied a lot. The relation between the cross ratio of the 2 intervals and this L is the time-like size of the torus. I'm putting 1 in the spatial size of the torus. And the relation between these 2 parameters is complicated, but the important fact is that this symmetry between x and 1 minus x is mapped to the symmetry of these 2 torus, changing the size of the torus by the inverse size of the torus. So this is the kind of modular transformation is related to this 1 to y minus x. And with this formula, you can just plug it into previous formula of the ranges in terms of this u function, and you get this expression that tells you that the U function is related to the partition function of the torus plus some logarithm, and the logarithm contains x times 1 minus x, so it's completely symmetric between x and 1 minus x. So if this U function is asymmetric and the transformation x, y minus x, it means that the partition function has to be asymmetric between L and 1 over L, so it means that there is violation of modular invariance. So you can produce this quantity. There is the asymmetry in the U function for the range 2 entropy, and this is equal to the asymmetry in the partition function under the modular transformation, where L and X are related by these functions. And one can ask why. Why, in simple terms, these two things are related? Because we say, well, this torus is equal to this torus because it's geometrically the same object, and you are doing a partition function of a Euclidean invariant Lagrangian, no boundary conditions, and then this should hold in most cases. But what happens if we, for example, we take a theory with some symmetry group and we restrict attention to the neutral algebra? So it means, for example, if you have a field, you are going to restrict attention to have only operators that doesn't have charge. How you do that? You, in the partition function, you do the same partition function, but now project to states that are neutral. So you have to put a projector that here you can think is this object that sum over the elements of the group of symmetry over all the elements of the group of symmetry and is normalized. So you have to insert a projector in order to go to the theory of the neutral fields. And this already kills this symmetry. It's not the same, this projector in this direction or in this direction. And on the algebraic side, what you have is exactly this non-local operator. Phi star is a non-local operator of the two intervals. So it's an operator that is not additive in the two intervals. So the same two things are connected. So in general, this asymmetry, how this partition function with this projection operator will depend on the cross ratio is complicated, but there is a particular limit in which this partition function will give you some number that is specific of the symmetry, is completely, let's say, geometric, and is specific of the symmetry, is universal in that sense. And this is the limit of high temperatures. How you understand that? Because you are inserting a projector, and then you can compute, for example, the partition function of your theory normalized by partition function of the complete theory. And this is giving you the expectation value of the projector that depends on the expectation value of all operators of the group. And in the high temperature limit, there are many independent fluctuations of all charges. And when that happens, the representation of these things tends asymptotically very fast to what is called the regular representation of the group. That is the same thing as to say that the expectation values of all twist operator, of all group operators is going to 0 except for the identity. So when you plug this information in here, you get that the limit of the ratio of partition function is just 1 over G, so it only depends on the size of the group. And with this information, you can compute the asymmetry in that limit, and the asymmetry has this difference of partition functions, and you take the large temperature limit, but you can equally well divide this, normalize it by the complete theory, because in the complete theory, these two things are equal, so they cancel the contribution of the complete theory. And this limit is is log 1g, that give you this. And this limit is the low temperature limit. And the low temperature limit, only the vacuum remains, so it's the same for the complete theory and your theory without charges. So you get this universal property that give you the log G contribution. In general, in 2 dimensions, there are more complicated cases, and the inclusion of algebras between a theory and the complete one has sectors or charges of non-invertible symmetries. This is more complicated. I will go very briefly through that. I will only say that you can also define dimensions for these charges, and there is another quantity that replaces the size of the group here that is called the index. The index is an algebraic construction that measures how different, the relative size between your algebra and the complete algebra. How many charges you have and the size of the representations. Well, and you go through the same calculation and you get that the limit of this U2 or the asymmetry in the limit of where the cross ratio goes to 1, that is the same in the partition function terms, is the high temperature limit. The limit of this asymmetry is just the logarithm of this index. And
high temperature limit in the interpretation of Renyi entropy, it's the which limit is
it's a limit in which the 2 intervals touch each other.
Okay, thank you.
Yeah. Well, this is nice, but it's still a little bit unpleasant or not very good, because you are somehow not talking about the model T, that is the one that you want to talk, but you are completing the model with some completion. They say you are thinking your model is inside one that is complete. But there is a way to say that this thing can also be expressed in terms of the model itself. It's not considering the index or the size of the inclusion of one interval on the complete model, but taking 2 intervals in the non-complete model and looking at the size of the inclusion of the 2 intervals on the non-complete model with respect to the 2 intervals in the same model, but now with the non-local operators. This inclusion, in fact, you have approved by Longo that these 2 things are related. This mu is the index of the inclusion of the 2 intervals algebras, and this lambda is the inclusion of one model with the other that is bigger, and there is this relation. In particular, for example, if this is complete, then the inclusion of the 2 additive algebra and the maximal algebra of 2 intervals is the same algebra, so it's 1. So this mu is 1 for the complete theory, and then you get that this lambda here is in fact the square root of the 2 index that is called the global index of the theory. So you can express it as a quantity that depends only on your theory with this index mu there. So in brief, yes.
So I wanted to understand this lambda. So I understand that dr are the quantum dimensions of the lines, right? Is d is the the quantum dimension.
Well, in this case, these dr's will be the products of the dimensions of the 2 chiral fields that you use to produce a field of the theory. You produce a field of the theory just putting together 2 chiral fields, and this is the dimension. Each chiral field has a dimension in this chiral algebra, and this here will be the product of the 2, and the ends the n's are the number of this type of fields that you have.
Which is not the capital N, though.
No, no, no. This capital N is just the fusion matrices. No. So what I mean here, I wanted to say that these dimensions are not integers in general, and you can get them from the eigenvalues of these fusion matrices. It's just a way to.
And sorry, in the little n, can you say again how is it related to the fusion algebra?
Well, no, this little n depends on the model that you have. This, in very concrete terms, this little n here will be the matrix in the partition function which you construct the model. I will go through that. So in very simple terms, what you get is that, for example, for a complete theory, you in the low temperature limit, you have a term that is given by the Casimir energy plus exponentially small terms because there is a gap between the vacuum and the next excitation. And then because of modular invariance in the complete model, you can say the same in the large temperature limit. So there is no subleading term that is not exponentially small because of modular invariance. But then for the non-complete model, this is changed by this different term, so you pick up a constant term in the expansion. So this is a way, it's a way to identify that the theory is not complete, directly looking at the partition function, so it depends on the spectrum of theory, nothing more than the spectrum of theory. And it's quite interesting that these mu's are, for example, they can only be some particular numbers, and then this partition function, these subleading terms can only be these indices. Well, this is I will go briefly through this. If you make the same idea for now ranges with more index, n equal to 3, instead of going, in this case, you go to the torus, and then for n equal to 3, you go to something with more genus, for example, this thing, and there is a symmetry in these three handles. There is a symmetry, and then if you think you have a complete model, you have this partition function, but for the non-complete model, you have to insert projectors along each of these handles. One of the projectors is redundant because if you put neutral things in these two handles, the other one has to be neutral. So it depends on just n minus 1 projectors, and in the limit of, let's say, large temperature, in the limit, in that particular limit where the two intervals touch each other, what happens is that you get two contributions, but the range entropy is divided by 1 minus n, so you get always, for all range entropies, the same contribution. Somehow this is called, in the literature, people call this a flat spectrum for these contributions. So how to compute this index in a practical way? Well, you start from the chiral models that you're using, and you have the chiral partition functions corresponding to different primaries. And then with these chiral partition functions, you can produce the modular transformations, and these modular transformations are linearly related to the same chiral partition functions, and the matrices here are called the S and T matrices. These are the modular transformation matrices. This is all very standard. And then your model is defined by a coupling matrix. It's the same, is to say that your fields now in 2 dimensions are combinations of chiral fields. And then the partition functions is given by combinations of chiral partition functions, and this is a matrix of integers. So modular invariance is the existence, that is the fact that these matrices here commute with the coupling matrix. In this very, let's say, explicit form, this is the modular invariance. T-symmetry, this T-symmetry, you can see that is related to the fact that that the different chiral fields have an integer difference, at least, of conformal dimensions, and this is necessary for the fact that these fields are causal now in 2 dimensions. They commute at the spatial distances. So this is not a new requirement, because I'm always thinking in a causal theory. And then you can compute the index in this way. That is this limit that we have been talking about. But you have this explicit expression, and you can define this for the chiral partition function. These limits are some dimensions of the chiral primaries, and then if you go to the calculation and do the limit, you get this. So you can obtain the index just by the coupling matrix and the dimensions of the chiral representations. And you can see that for a complete theory, modular invariant theory, this is going to be equal to 1. And it's going to be different from 1 if you don't have modular invariance. What are these models? Well, for example, this is the Ising model, the least central charge, C equal to 1/2. And this model, for example, you start with a stress tensor. And you can add fields in order to complete the theory. And you can, in fact, add in different ways to get a bosonic theory that is called the Ising model. And here is just a fermion field. So there are 2 different completions for the same stress tensor. And you have intermediate models. Here, for example, is just a one chiral fermion. The other chiral fermion here is just these 2 bosonic fields. And the next model is this one that also have a fermionic and a bosonic completions and a lot of submodels. Each of these submodels have a particular global index, this mu that is written there. You can see here these strange numbers. Here is just a 4. And these lambdas are the relative index of the inclusion, for example, here the stress tensor and this other one. This is lambda, is the relative index, and this is the global index that depends only on the model and not the inclusions. And are all related by this longer relation between the global index and the index of inclusions. The next one, C equal to 4/5, has 3 completions, 1 fermionic and 2. One is called the diagonal completion, and the other one is called the non-diagonal completion. This one has fields. These are only scalar bosons, and this has some boson with a spin. It is interesting that in 2 dimensions, a given model can have inequivalent completions, more than 1 inequivalent completions. In dimension greater than 2, the completion of calculated violation for 2 balls, for 2 intervals, the equivalent of for 2, or in fact, infinitely many disjoint regions, is only unique. It's unique, and is the relation between the unique completion and the model is always a group. This is called the D-H-R theorem. That is a theorem that is quite old in mathematical literature around the 90s, or the 80s, 90s. But in 2 dimensions, there are many possibilities. And one thing, well, maybe if I increase the central charge more and more, I will have an enormous, like, tree of graphs. But in fact, it's not like that, at least for models with C less than 1, these minimal models. In fact, generically, you get some finite number of submodels, eight submodels. Here I'm looking only at submodels of the diagonal completions. This is in a paper with Valentin Benedetti and Javier Magan of the last year, where we obtained this model looking at the subalgebra of the fusion rules for the minimal models. And there is an older paper by Kawashigashi and Longo where they classify all the possible symmetries that in this language are called tensor categories that you can have in each dimension. But it can happen, for example, that for some particular symmetry, you can have more than one model. So we classify the structure of submodels. And here is some models for the case of diagonal completions. And then I will show a simple application of this. Suppose that you have one of these theories for some central charge, and you want to make a renormalization group flow, and then you excite the theory, you put in the Lagrangian some operator, some relevant operator of the theory. You have to pick up one, and then you want to go to infrared and to know something about that. Well, you can say that the renormalization group flow is taking place in the stress tensor of the original theory plus the excitation that you put in the Lagrangian. So if you pick a particular scalar and the stress tensor, you can say, well, what is the minimal algebra that these two things generate? And for example, here, if I take some particular field of this submodel, it will generate something in this submodel. So I can think, well, what is going on is something that I can study only in the submodel and this normalization group flow, and will end up in the infrared to somewhere else. But what is preserved? Is preserved the symmetry that is up of this model. So this model will be like the neutral part, and then you have some charges from going from this model to the higher models. You have some charges that have to have some representation in the infrared because the symmetry is going to be preserved along the normalization group flow. And then it must be the case that the structure of the tree above the model, the submodel, has to be preserved in the ultraviolet and the infrared. And for example, a simple case that you can study is, for example, here, there is a famous renormalization group flow studied by Samológico some time ago, where you excite with this particular field, and here, that is one of these algebra here. And you can see that you have to respect in the infrared the same global index, and the same structure up in the diagram. And if you look at the models with central charge less than 1, because it has less than this, the central charge of this, because of the Samológico C theorem, the central charge has to decrease. The only case that has the same index is this other model that happens exactly for m one integer less. So this can run only to m minus 1, let's say, and to this particular model. And if you see the structure below here, all this structure in black does not respect that the indices are not the same in the ultraviolet and the infrared. So you can say that the explicit term that you added to the Lagrangian kill all this part of the symmetry, and in the infrared, all this part of the symmetry is emergent, is a new one, it's different. But the upper part match exactly. This is a particular case, and you can study also non-diagonal models. Yes.
So to understand, the rule to construct all these different models is that they have to be closed under fusion of operators. That's the rule that you're using to construct them.
Yeah. So what we did is just to take the fusions of the complete minimal models that are in the literature and look up to subalgebras that close in itself, and this gives you this. Kawashi-Gashi and Longo work is more complicated. I cannot tell what this is. So let me, well, all this was finite. Index is lambda, this mu are finite numbers. It's like, for example, the case of a group where the dimension of the group, the size of the group is finite dimensional. But what happens when the relation between the model and the submodel, for example, in order to complete the model, you have to put an infinite number of operators. Well, in that case, the index is infinite, right? And in that case, for example, a typical case will be the case where you have a relation between the model and submodel, which is a Lie group. You take a Lie group symmetry and you restrict attention to the chargeless operators. And in that case, it can be studied. We studied, in fact, in any dimensions here. And the difference is that, for example, before the high temperature state was giving you 0 for all group operators except for the identity. Here, you have to take into account that this is continuous. There is no, you have group operators very near the identity, and you have to make a calculation. And it turns out that you also get something completely geometric or algebraic or universal as you go to the limit of high temperatures, and this ends in terms of, instead of giving you the index finite number, give you something divergent in the form of log-log divergences. And the coefficient here is just the size of the Lie algebra. For example, for the chiral scalar, the case of I showed before, you can compute exactly the range entropies, and the limit give you this. And this is 1/2 tell you that this is a kind of orbit fall under a U1 symmetry, and it's exactly what you expect because the chiral scalar is just the U1 neutral part of the free fermion. For the Virasoro net, for C equal to 1, if you compute with the partition function, you get this 3/2 here in log-log. 3/2 means that there is 3 generators in a Lie group, and this is exactly what Reren found in '93, that the Virasoro net for C equal to 1 is a fixed point of the chiral algebra of SU2 level 1 divided by the global symmetry group, that is an SU truth, so it has 3 generators. And you can also compute the range entropies for C for the Virasoro net. It means only the stress tensor, so it's not complete, the theory. It has too many sectors, and it diverges more strongly than this log-log expected for a Lie group. Of course, it's not a Lie group in that case for C greater than 2. But in that case, well, I will not talk much about that, but we suspect this result because it's kind of strange that it grows, for example, with the central charge. It still grows with the central charge where you only have one field that is the stress tensor. So something seems to be not going well in the idea that you can map the range entropies to these partition functions. In that case, and there is a reason, is that there is something that is called, this particular model doesn't have something called strong additivity, that the algebra of 2 intervals do not add up to the algebra of the bigger interval. So something strange, and we do not know how to compute in a reliable way now the ranges, even the range 2 for the stress tensor alone in C greater than 1. So maybe I would stop here if there are questions, because I have until 45, right? This is my time. Okay. See if there are some questions. So these are some ideas for higher dimensions.
I understand. So if mu equal to 1, Ag's, you have a modular invariance, and Ag's duality is not broken. You have max.
When you have modular invariance, you don't have duality is not broken.
It's not broken. But then in the Ising, so this is a confusion. The Ising model, for instance, the original one, in which modular invariant, so Ag's duality is not broken, but we do know that as global symmetry, which means non-local operator, topological non-local operator, no? Z2 and the Kramers-Vanier duality. So, I mean, typically to claim absence of symmetries, we believe you need to inject quantum gravity and, more complicated. Gravity is important, no? So I'm missing the point here. Yeah.
Perhaps the confusion is the following. Suppose you have let's say, a free fermion in 4 dimensions. Is complete, the theory is complete, but it still has a symmetry, the U1 symmetry. So when I'm thinking that there is in that case, I will go directly to think in the neutral part. And the neutral part is the one, so now I'm taking the current, for example, the stress tensor, but not the field, and this has Hug duality violations. So when I'm thinking that high duality violation associated to symmetries, I'm thinking in that terms, in the terms of the neutral part, let's say. Perhaps this is a confusion.
Yeah, it's not because the completeness. You may know that in quantum field theory, the claim is that the absence of global symmetries are related with the completeness of the spectrum.
The question is about
also
this idea of quantum gravity.
Yes.
The quantum gravity forbids symmetries.
Yes.
Okay.
Yes.
Well, this idea is a completeness that is somehow exactly what people would say about, for example, gauge theories. When it's complete, when you have enough charges, this is going to be mapped to Hug duality, and if you do the same for regions that are disconnected, this Hug duality just tell you that you can have global symmetry, but you have to have the charge operators too. You cannot restrict to the neutral model, right? In that sense, it doesn't exactly match the idea of that you one expect to quantum gravity thing, this idea of there are no symmetries, right?
So about this last thing that you said, I'm not sure if I understood correctly. So I saw that this asymmetry parameter, let's say this asymmetry function U2, or well, I guess anyway, the scaling of this thing was, for the finite group, it was going to a constant. For the Lie group case, was going to log of log. And now in this last case, it was going to an actual log. So, okay, first of all, what is this Virasoro-net you were saying? And secondly, should I visualize this as the completion being somehow having a cardinality even bigger than a Lie group?
Exactly, that's the thing.
So what's beyond a Lie group that I can think of?
Something that is what is beyond the Lie group? You can say, well, I have an algebra with charges and the subalgebra without charges. Here, the subalgebra without charges is the stress tensor, and the other one is something, for example, something with C equal to 2, but complete, right? But this theory will have infinitely many primaries, right? In the case of the Lie group, also have infinitely many primaries, but somehow tame, and you can compute it, and it's just particular log-log thing, right? In the other case, you have much more charges that the one that give you a Lie group, let's say, something like that. And the Lie group is replaced by the Lie group that you use to go from the big model to the smaller model. Here is replaced by something called a conditional expectation, something more general that can take an algebra and go to the subalgebra. Some channel in terms of quantum information that take an algebra and goes to the subalgebra.
Okay, but so...
But more specifically what it is, I cannot...
okay,
no, in that case it's quite open in the sense that there is this strange property of that is not a strong additivity. If you have two intervals, for example, you say, well, I have a charge and anti-charge, and the full interval. So each interval have charge and anti-charge, but not have charges. And when they touch, they have charge and anti-charge. And still you can produce it with the two intervals that touch, because you can put charge, anti-charge, and these two, when they touch each other, they can kill each other and produce the charge, anti-charge for the full interval. This is a strong additivity. But when you have too many sectors, somehow, as a stress tensor for C greater than 1, somehow this is not going to work anymore. So there is something more in the big interval that is not in the touching interval somehow.
Okay, I see. So it's like an even bigger restriction, as you say, I think, from a whole set of primaries to a stress tensor is some reduction in cardinality that is...
Yeah, it's not strictly cardinality because...
Yes, I know it's not the right word, but just to help the intuition.
It's the same idea, yeah. You have a bigger amount of... Yeah.
Okay, thank you.
In your analysis, is unitarity used, or is it completely unnecessary to rely on unitarity?
All that I talk about is about unitary theories, or unitary quantum field theories, right?
But do you use it manifestly somewhere? Assumptions?
Everywhere, I think, because I'm talking about algebras of operators and causality, and I don't know, well, maybe you know, but I don't know how to think about, for example, it's important that in this thing, modular invariance, conformity, there are also this aspect of statistical models that can be non-unitary, and people think about modular invariance in that cases too. But in that case, I do not know how to think about a quantum field theory to define algebras, or when I'm saying I have algebras, I have a reflection positivity because the operator correlators should satisfy positivity, right? And this is unitarity. So,
okay,
for example, the central charges are restricted to the ones that give you unitary models, right?
Okay, I think I understand perspective. I think it just looked, the definition of the index can just formally used, but the whole philosophy and the...
Right, but I could not talk about range entropies, for example. I do not know how to do it.
Okay. Yeah, thank
Perhaps Tadashi was talking about something more...
Yes, he was talking about non-unitary.
Yeah.
So if I understand correctly, in these models that you discussed, no? So I would say that those are defined by the fact that they're closed under a fusion. And you talked about modular invariance, say, of the partition function. Do you know what happens about crossing symmetry if you compute 4-point function? Do they also violate crossing symmetry?
No, I don't think so. No, the 4-point function of the operators should satisfy all, because of locality and positivity, all these relations. So there is no... One thing that is related to what you say that is that the range entropies are usually thought about as expectation values of some twist operators in the boundary of the intervals. And if you express it in that way, the range entropy of two intervals can be related to a 4-point function correlator. And people in the past have said, well, automatically this satisfies crossing relation, and this crossing relation gives you the ux equal to ux minus 1. So, and they say, well, then unitarity, crossing relation, gives you the idea that the range entropy of complementary regions are equal. It coincides with that and coincides with modular invariance. But this change of chain of thoughts is not correct, because when there is no modular invariance, there is hard duality, you really cannot think of the twist operator. The twist operator exists, but it's a non-local guy. It cannot be thought as field operators in the boundary. So this is not correct. So this somehow, there are some papers that say this property of the range entropy implies modular invariance. That implies that modular invariance comes from unitarity of the theory, for example. This is a statement that you can find in the literature. And the error in that reasoning is that these range operators cannot be written in that case as local operators in the boundary of the intervals.
More questions? Okay, if not, let's thank Horacio again.